Alright, today I'm going to show you a theorem that has to do with modular arithmetic, which we've been talking about for the last few days. It's called Fermat's little theorem. It's not related to Fermat's last theorem. We are not touching that, believe me. What Fermat said about modular arithmetic was, let's take any prime number and make that my modulus. And if I pick another integer, a, I'm going to call it a, and as long as it's not a multiple of p, then this rule will apply. Well, if all of those requirements are met, then a to the p minus 1 will be congruent to 1 mod p. Kind of a powerful theorem, kind of a confusing theorem when you read it at first, but let's talk about an example of how this works. So let's say I've got my prime number, my prime modulus being 7. And since I'm dealing with modular arithmetic, I can let a be 1, 2, 3, 4, 5, or 6, but I can't let it be 0 or any multiple of 7. So I'm just going to use these 6 numbers. And any other number that would be bigger than 7 is going to be congruent to one of those 6 numbers, 1, 2, 3, 4, 5, or 6. So basically I'll have covered everything by covering these 6 numbers. So I'm going to raise each one of them to the 6 because that's what p minus 1 is. I'm going to raise each one of them to the 6 and see if it's actually congruent to 1. Well, 1 to the 6 is 1. That's easy. 2 to the 6 is 64. And I know that 7 times 9 is 63. So 63 is a multiple of 7. So 64 will give me a remainder of 1. Looking at 3 to the 6, that's 729. I know that 728 is a multiple of 7. So 729 will give me a remainder of 1. If I think about 4 to the 6, that's basically 2 to the 6 times 2 to the 6, and I've already figured out 2 to the 6. That's 1 mod 7. So 2 to the 6 times 2 to the 6 would be 1 times 1, so 4 to the 6 is basically 1 mod 7. If you didn't know that, you could just divide by 7 and figure out what the remainder is, and it'll still be 1. 5 to the 6 gives me some huge number, and that's going to give me a remainder of 1 when I divide by 7. 6 to the 6 is going to do the same thing. Alright, so I basically checked all the numbers between 1 and 6, mod 7, and they all give me a remainder of 1. You could try that with any prime modulus and you'll get the same result. I just tried 7 because it's nice and small, but it still involves some work. So let's say I wanted to find the remainder when I divide 7 to the 86 by 13. So here's what I'm going to do. I know that 13 is prime and 7 is not a multiple of that prime number, so I can use Fermat's little theorem. So here's what I do. I take 7 to the 86. Now I know that since my modulus is 13, then 7 to the 12 is going to equal 1, according to Fermat. So I'm going to take as many 7 to the 12s out of 7 to the 86 and then deal with whatever's left. So 7 to the 86 is the same thing as 7 to the 12. Raised to the 7, I can take 7 of those. I can divide 7 of those out, leaving me with 7 squared. So each of those 7 to the 12s is congruent to 1 mod 13, and 7 squared, that's just 49. So the whole thing is worth 49 mod 13, and if I divide 49 by 13, the remainder will be 10. So the remainder when 7 to the 86 gets divided by 13, the remainder is going to be 10. All right. We can also use this for solving linear congruences, which we talked about a couple of videos ago. Solving 5 to the x is congruent to 3 mod 17. So here's what I do. It's kind of a tricky thing, but I'll show you how to do it in general. I'm going to multiply both sides of this congruence by 5 to the 15. And watch what that does. That 15 seems arbitrary, but it's actually not. What that does is it gives me 5 to the 16 times x on the left-hand side, and it gives me 5 to the 15 times 3 on the right. But since my modulus is 17, then any number raised to the 16, as long as that base is not a multiple of 17, any number raised to the 16 is going to be congruent to 1 mod 17. That's why I put that 5 to the 16 on the left, so that I know that that's congruent to 1. So all I have on the left is x. And what I have on the right is 5 to the 15 times 3. And I just have to figure out what that is, but once I do that, I'll have my x. So I figured that 5 to the 15 is the same thing as 125 to the 5th, and the 3 is still a 3. 125 mod 17 is the same as 6, because when I divide 125 by 17, I get a remainder of 6. So 125 and 6 are congruent mod 17. So I'm just going to change all my 125s to 6s. And then I'm going to pair up the factors and simplify each one. So 6 to the 5th times 3 is the same thing as 6 times 6 times 6 times 6 times 6 times 3. And if I reduce each of those down, mod 17, each of the 36s becomes a 2, and the 18 becomes a 1. And so I'm left with 4, mod 17. Now, if you want to know what to do in the general case, when you've got something times x congruent to a number, mod p, and p has to be a prime in order for this to work, remember. What I'm going to do, remember I want to get a to the p minus 1 over here, and right now I've got a to the 1. So what I do is I multiply both sides by a to the p minus 2. And so that's going to create a 1 on the left-hand side. All right. We can also use this, we can use the contrapositive of Fermat's little theorem to show that numbers are not prime. So here's what the contrapositive looks like. If a to the n is not congruent to a mod n, then n is not prime. Okay, so that's the contrapositive. Look back at your geometry notes to see what the contrapositive is and why that's correct. So we're going to show that 63 is not prime. I already know it's not prime, but I'm just going to use this theorem to show that it's not. So I'm going to let a be some number that is not a multiple of 63. Any number will do, so I might as well just use 2. If I used 1, then I would actually disprove what I wanted to prove, so I'm going to use 2. 2 to the 63, I'm going to show that that is not congruent to 2. Okay, so 2 to the 63 is the same thing as 2 to the 6 to the 10 times 2 to the 3rd. All right. And so 2 to the 6, 2 to the 63rd then, mod 63 is congruent to that same expression, mod 63. So now I'm just being more specific and talking about 63. The reason I chose 2 to the 6 to take out a bunch of times is because that's congruent to 64. 2 to the 6 is 64. And the reason 64 is nice is because when I divide that by 63, I get a remainder of 1. So 1 to the 10 times 2 to the 3rd, that's just 8 mod 63. So 8 is not congruent to 2 mod 63, so my original 2 to the 63rd is not congruent to 2 mod 63, therefore 63 is not prime. Okay, so that's how you can use the contrapositive to show that numbers are not prime. And that's basically Fermat's little theorem. If you have any questions, email me, Facebook me, and I will see you tomorrow.